Hello everyone, my name is Ajay Kumar Dakar. So this is my slideshow presentation for assignment number 5 of course Advanced Database Systems. So let's look into the slides. So in these slides I am broadly going to talk about four topics. One is concurrency control and others are multiple granularity, weak levels of consistency and snapshot isolation. So in the assignment like it was told to talk about only three topics, but I have added concurrency control also because all the remaining three topics are the part of concurrency control schemes only. So let's look into this topic. So what is concurrency control? So concurrency control refers okay, so concurrency control refers to the simultaneous execution of transactions without conflict. So why we are executing this simultaneous transactions? Because only to increase the throughput of our system and also to reduce the response time. So it is necessary to execute more than one transaction because in the real world scenario, we don't want to delay anything. Just we want to execute many things at the same time. So what are the key objectives while executing multiple transactions in our database system? So the four key objectives that we want to maintain while executing in our database. So one is atomicity, so that means either whole transaction occur, nothing occurs. One is consistency, so at like inconsistency, so our database should be in a valid state, like it should not break any valid state. Like let's say what I mean by invalid state. So let's take an example of a bank. So in example of bank, let's say one user transfers money from his account to the account of another account in the same bank. So typically it means that the total amount of money in that bank should not increase or decrease because it is only transferring. So after executing more than one transaction, uh, like let's say and there are more than one transaction which are executing the transfer of money from one account to another. So while executing those transactions, so total amount of money in the database should not increase. uh, Simply it means like it is valid that it should not increase or decrease. So that is the consistency, that thing I can say that that is the data integrity of the database system. So by meaning of consistency, we should not be able to break the data consistency, data integrity of that database. So consistency means that thing. Third one is the isolation. So in isolation is transaction must be unaware of another transaction. The execution of other transaction should not affect the execution of my current transaction. And another is durability. Should this our scheme should be able to handle the system failure also. So in this concurrency control schemes, like we already have looked on various logs already, like shared log and exclusive log. In shared log, where whenever we put shared log on a data item, we can read whenever we want to read a data item, we need to put a shared log on the data item. Or also, whenever we want to read or write something on a data item, then we need to put a exclusive log on the data item. Okay, so before we have already talked about two-phase locking while talking about the concurrency control schemes. So I'm not going to talk about like two-phase locking here, but let's look on the multiple granularity, like how we are going to do maintain concurrency on multiple granularities by multiple granularity scheme. So what is multiple granularity? So in multiple granularity, here granularity means the size of the data items on which we are going to put. So in this scheme also we are going to put a logs on the data items, but here we are doing many things differently. So let's look. So so in this, like we have divided our database hierarchically into blocks that can be logged and tracked. So how we have divided our, so this is the simple like breakdown of our database into four levels. So first level is the database itself. Then a database can have many areas. Then each area can have many files, and each file can have many records. Okay, so in this way, we have broken down this whole database. So what we are going to do, like we can put lock on any of these nodes, either shared or exclusive lock. We can put on any of these nodes. Like if I want to lock all these records, then I can simply put a shared or exclusive lock on this node. And also, if I want to put all these records like of f files, file a and file b, then I can simply put a lock on area 1. Okay, so this was the broad talk about this multiple granularity, but let's look on these points also. So it allows to lock data items at different levels, and when any node is locked implicitly, all descendant nodes are also locked. uh, and also locks are applied hierarchically. So hmm. So about this line, I am going to talk later on next slides, while talking like how we are going to put locks. And also this is an efficient locking strategy because it avoid conflicts between locking. And how we are going to avoid conflict, we are going to look into this on next slides. So let's talk like how we have divided our granularity levels. So first level is database, then area, then files. So I have already talked about this. I have mistakenly rewritten this line, locking database implicitly. I might have copied before slides and pasted here mistakenly. So I need to remove, but I forgot. So in this example, I am talking about this part, like how we have divided into multiple granularity levels. So here the coarse granularity. Granularity means the size of the data item. So types of locking. In the types of locking, like we have already looked on two types of locks, but in for this we have introduced another three types of locks, which are intention shared and intention exclusive. So why I have introduced these types of locks? Let's say one transaction is already having a exclusive lock on RB1. Okay, then another transaction comes and it wants to lock whole and this whole area. uh, that transaction wants to put exclusive lock on this whole area. So what it will be going to do, it will put exclusive lock on here, but before that it needs to check that any of this node should not have either shared or exclusive lock. But how it is going to do, like this, these are loads of nodes, so it can increase our overhead too much. So how we are going to handle these things? So we are looking for that thing, we have introduced the intention shared, intention exclusive, and shared intention exclusive locks. So what does intention shared means? That means if we have put intention shared lock on any node, then any of the lower level data item under that node can have a shared lock. Okay, and if in intention, if we have put intention exclusive lock on any node, that means any of the lower level node under that node can have a shared or exclusive locking. Okay, and in shared intention exclusive, like we have if we have put shared intention exclusive lock on any node, that means we have put the shared lock on that node, and any of the level node can have a exclusive locking on that node. Okay, so let's look here. So let's say I want to put a lock, exclusive lock on here. So how I'm going to execute, like how I'm going to put exclusive lock here? So to put a exclusive lock here, I need to traverse from the root node to put the exclusive lock here. While traversing from root node to that node, I need to put intention exclusive lock on this ancestors also, to be able to know that this node is having exclusive node. Okay, so while traversing, if I want to put exclusive lock here, then I need to put intention exclusive lock here, then intention exclusive lock here, then exclusive lock here. Like if I wants to put a shared lock here and exclusive lock here by same transaction, then what I am going to do, I'm going to put a intention exclusive lock here, then SIX lock here, that means shared intention lock here, shared intention exclusive lock here, then here intention exclusive lock here, then exclusive lock here. I can, okay. So I'm going to put IX lock here, SIX lock here, and IX lock here, and then X lock here. That means like I by the transaction wants to put a shared lock here, then and exclusive lock here, then it will going to put locks in this way. Like it will put IX lock here, then SIX lock here, then IX lock here, then exclusive lock here. So I'm going to talk about these steps in the next slides, but I've explained here only to better understand these points. So okay, so in the types of locking, like we have introduced intention locks. So intention locks are introduced in addition to shared and exclusive lock. If a node is in intention mode, then explicit locking is done at lower level. So here I have shown, like if I have already put intention exclusive lock here, then that means that uh, any of the lower level node can have a exclusive lock here. So that means okay. So that is the meaning of intention lock, and it allows high level node to be locked explicitly without checking all the. Hmm, this point should not be here. Uh, hmm, like I have already explained this part. That point means that, like if I wants to put exclusive lock here, then I need to note that any of this node should not have exclusive lock. But let's say this was the transaction T1. So for transaction T1, I have already put the locks. Now transaction T2 comes and it wants to do the exclusive lock here. So what it will do, it will how it will be going to check that any of these descendant nodes will not have exclusive lock or shared lock. So by simply if there is SIX lock, then it will see that it is already having SIX lock. Then any of the descendant node will have exclusive lock there. Then that new transaction should not be able to put exclusive lock here. So that was the core principle, like why we introduced this intention exclusive lock. So to reduce the time consumed in checking that any of this node is not having mm, exclusive lock. Okay, so that points means that thing only. So intention nodes are put on all the ancestors of a node before the node is logged explicitly. I have explained. Three additional logs we have introduced: intention shared, intention exclusive, and shared intention exclusive. So in shared intention activity, we that means that we have put shared lock on that node, and any of the descendant node will have exclusive lock. Okay, that node is explicitly locked in shared mode, and explicit exclusive locking is being done at lower level. So what are the locking rules? So transaction must lock root node of uh, node in any mode. So like about this rules, like this thing I have copied because I wasn't able to form these rules by my because I already know that how we are going to put lock on any node, but I don't know the exact rules, like what rules we should follow while locking this. So I have taken these rules from the Geeks for Geeks website. So let's look on to this point. So transaction must lock root node of any node of the node in any mode. So while locking any node, we need to first lock this root node in either intention shared or intention, any of that intention intention lock, and we need to traverse by from root to that node. Okay, so if transaction Ti can lock a node in S or IS mode, the only if Ti currently has the parent of the node logged in either IX or IS mode. So that means if I have put I wants to have if I wants to have shared lock here, then its parent should have intention shared lock. And if any node contains shared or intention IS lock on that node, that means its parent should have IS or IX node, IS or IX lock on that node. That means that thing only. Transaction Ti can lock a node in X, SIX or IX node only if Ti currently has the parent of the node locked in either IX or SIX mode. Transaction Ti can lock a node only if Ti has not previously locked any node. That is, Ti is too fast. Transaction Ti can unlock a node only if Ti currently has none of the children of the node lock. Okay. Transaction must follow the below compatibility chart. Like if the some node is already having any of this lock, and let's say any of the node is already having IX lock, and I am going to put a shared lock on that node. So whenever another transaction tries to put a shared lock on that node, it simply uh, uh, like the transaction simply aborted, because we are not allowed to put a shared lock on a node which is already holding a IX lock there. Okay, so this is the compatibility chart we need to maintain while putting locks. So, and these were the rules, like these are the simple rules. Like if we wants to put a lock on any node by X, SIX or IX dot, then its parent should have either IX or SIX lock. Should have, it should have, simply. Okay. And if a transaction Ti can lock a node only if Ti has not previously unlocked any node. That is the two-phase locking. Like we need to put in two-phase locking, like we already have talked, like to a transaction can simply in the first phase it simply puts a lock on all the data items, then in the second phase it simply like removes the locks. If transaction has removed some lock, then it cannot put lock on any of the data item. So either the transaction can only put the lock on any data item, and or transaction can remove the lock on any data item. It should be like it can put remove. It cannot do that thing. Either in the single phase it can put the locks on all the data items it needs to lock, and in the second phase it needs to remove all the locks on from the data item. So this was the simple rules. So let's take an example, like hmm. So what is, let's say transaction T1 to lock FA in exclusive mode, A1 in shared mode, we need to traverse from root node. Okay, so transaction T1 wants to put exclusive lock or X lock on FA, X lock on FA, and shared lock on A1. That means transaction T1 wants to put shared lock on all this. Shared lock on A1 and exclusive lock on FA. So how it is going to do? It will simply put a IX lock here. Like it will traverse from the root node to that node. It will come here, put IX lock, then it will come here, put SIX lock, then it will come here and put X lock. Okay. It simply have done the locks on all the data item. Now transaction T2 comes. What transaction T2 wants to do? It wants to put a RC1 lock in shared mode. RC1. So transaction T2 wants to put lock in shared mode here. So what it will do, it will simply traverse from the root node. From the root node, on the root node, it will put. It wants to put IS lock here, but there is already IX lock. So from the compatibility chart, we will see that IX and IS are both are compatible. So it is compatible with it. So it will not do anything, and here it will come. So there is no lock on this node. So it will simply put IS lock here. Then it will put IS lock here. Then it will simply put shared lock here. Okay. So transaction T2 has also successfully locked the data item. Now transaction T3 comes. So what transaction T3 wants to do? It wants to lock RA1 in shared mode. So what transaction T3 wants to lock this node in shared mode, but it cannot, because technically it cannot, because they like transaction T1 already holds the exclusive lock on all these data items. So it should not be able to take the shared mode lock. So how we are going to do the in this multiple granularity rules. So it will simply traverse from the root node and reach here. So what transaction T3 will do, it will simply tries to put is lock here, and we will see that is and ix both are compatible with each other. So it will comes to next node, and here also it will tries to put is lock here, and it will see that six and is both are compatible with each other. So is and six both are compatible with each other. Now it will come here and it will tries to put is lock here. So when it tries to put is lock here, and it will see that there is already an exclusive lock here. So if we see by compatibility chart, is and x both are not compatible with each other. So simply so here I have written also like is is not compatible with x on FA, hence it will be reverted back. So simply transaction T3 will be reverted back here. So now let's talk about the weak levels of consistency. Before we are looking, we have also talked about the serializability. In the serializability, uh, if the transactions are serializable, then that is the highest level of consistency. That cannot serializable transactions cannot block any of the data integrity of our database. So that is the highest level of consistency. So it is maintaining its consistency. But in the real world scenario, like to maintain the whole consistency, it is it is too much time consuming, or we can say too much processing for it. So there is too much overhead to maintain that consistency. So for that thing, also like there are many examples where we don't need to maintain that much of consistency. Let's say we have talked about read write conflict. Okay, so read write conflict, yes, it is a conflict, but let's say some transaction wants to write on, like let's say for example, take a example of a class. So if we take an example of a class, so we need to maintain the average marks of the class. So let's say currently some teacher is putting marks on the database. So uh, okay. So at any point of time, if any other teacher wants to read the average marks of the class, so we should not able to hold the transaction before to maintain serializability and all that thing, because because it is taking only the average marks of the class. If it breaks the consistency also, so there is no effect on our database. It is simply reading the database, so it is not writing anything. So let's say transaction T1 wants to okay, let's understand this example clearly. uh, hmm, okay. hmm. Let's say transaction T1 wants to read that number of students, total number of students in the class. Okay, transaction T1 only reads the total number of students, and transaction T2, what it reads, not the total number of students, but it reads, let's say it is adding some student, it is adding one student, adding one student, okay. So while adding this, these both transactions are happening concurrently. So to there is no need to maintain serializability here, because it is not necessary to maintain. So it can break. Like while adding here in the middle of the transaction, it is showing some other results or false results also, but we don't need to break this thing. Okay, so it should be able to read the total number of students, because that transaction only wants to we can only need to have a approximate about it. So for that thing, we should not hold this transaction. Like in the concurrency control scheme, it will try to put lock, but it will not be able to put lock on number of students, because this transaction is already having a lock here. So this transaction will be on hold. So it is not necessary to put a hold on this transaction, because it is simply we don't want to maintain consistency here. Okay, so here this example shows that maintaining a consistency is not that big requirement. Okay,
So here I can say that all the read transactions which are reading should not be put on hold just because some other transaction is having some changes there. So we don't want to have maintain consistency there. So we can trade off somewhere, like we can reduce our consistency to increase our speed. So if this transaction is allowed to read like without putting lock, then it will simply read that thing, and the speed of our database simply increases. And also there is a I can say that this is like a fight between, like, we can increase the consistency in our database, or we can increase the performance of our database. So both cannot be increased simultaneously. We can trade off with each other, like by decreasing the consistency, we can simply increase the performance of our system, or we can or either if we want to increase our consistency, then we need to decrease our performance somewhere, because to maintain the whole consistency, we need to do a lot of overhead operations. So only these things I have written here, like levels of consistency are trade-off between performance versus consistency. In lower degrees, it provides approximate information about the, like, it only shows the approximate information of our database, not the exact, like it is not in consistent mode, so it will not show the exact database. Okay. So for example, for calculating average marks, this thing I have already told about, like it is not necessary to estimate accurately. An approximate figure is enabled. Here we can improve performance. So here we don't need to maintain a read-write consistency with each other. So here we can increase our performance. So levels of consistency. First is the serializable. That is the strongest level of consistency, but it is highly overhead type. Like we need to do lots of operations to maintain that serializability. Okay. So next one is the repeatable read. In this repeatable read, only the in any of the read statement, only committed records will be read, but repeated read must return the same value, even if the records are inserted in between. Okay. And in read committed, this means that only the committed records can be read, but successive read may vary. And in read uncommitted, even uncommitted records may be read. So these were the levels, but in the real world scenario, like if you talk about Oracle or PostgreSQL, they also have one. They also follow one weak level of consistency called snapshot isolation, which is not mentioned in like SQL standards, but they are following that thing to increase its performance. Also, it is very easy to implement. So Oracle and PostgreSQL by default support a level of consistency called snapshot isolation. So it is also not the highest level of consistency, but it maintains consistency in most of the case. Like it is very rare case that where it breaks the consistency. So let's look on more snapshot isolation. So what is snapshot isolation? So it is weak level of consistency that I already talked. And let's say transaction will see same state of database throughout their operations. It reads the last committed values that exist at the time it started. For example, so in snapshot isolation, like if this transaction starts, so what it will do, it will take a snapshot, like uh, it will simply, in simple language I can say, it will take the picture of whole database into its local memory, and if then it will do any change on the database, so that will be stored in its local memory, that will not be visible to other transactions. So here transaction T1 starts, so it will take the snapshot of the database, that is X variable contains 100 and Y variable contains 200. So it will simply read 100, read Y 200, and write X plus 50, and write Y minus 50. Okay, so this writes statement, so it will simply write on its local variable, not in the database. It will be written on its local variable, then it will commit. In the meanwhile, transaction T2 starts. It also takes the snapshot of here. So here it has already changed the value of X and Y, but while reading the values of X and Y, it will simply take 100 and 200 because it has already taken the snapshot of database. It will not going to look into like what has happened after taking the snapshot. So that's why it has written only 100 and 200. Here I have explained also, like x and y both are uncommitted, still it reads the value which are present at the time to start the transaction. So at the start of the transaction, it has already taken the snapshot which contains the 100 and 200 value. So it will simply read here 100 and 200. Okay. So while reading, it takes the snapshot, then it does the changes in its local variables. Then while committing, it simply commits only the variables which has been changed. Like here, it has done write statement on x and y. Then while committing, it will check that any of the other transaction has changed something on this x and y variables only. Okay, so it is in snapshot isolation. Like one thing I can mention here that it uh, it does not allow the write write conflict, but somewhere it allows the read write conflict. Like in the skew write problem also, it allowed the read write conflict. That's why it breaks the database consistency. But we are going into this those things in next slides also. So what are the steps of snapshot isolation? At the start, it takes the snapshot of the whole database. Then each transaction reads and updates the value in its snapshot, and updates of the other transaction will not be visible to itself, and commits only if no other transaction. So it is very important line, like commits only if no other transaction has been written on the data it is writing. Okay, let's take an example. So here T1 starts, and in the next instruction T2 starts. So both has taken the snapshot of the database. Okay, what transaction T1 is doing? It is transferring 50 from Y to X, and what transaction T2 is doing? It is transferring 40 from X to Y. Okay, this is a simple bank database system. So it is simply means transferring 50 from account 1 to account 2, and transferring 40 rupees from account 2 to account 1. Okay, so what transaction T1 will do? It will simply read values of X and Y. Then it will on X it will write X plus 50, and on Y it will write Y minus 50. Then it tries to commit. So while trying to commit, it will see that it is writing on only variables X and Y, and no other transaction has currently changed the value of X and Y. So here it means that only if no transaction has been written. So here it successfully commits the transaction because no other transaction has written anything on variable X and Y. Okay, then now transaction T2 executes. So what it will do, it reads the value of X and Y. So what it will read, it will simply read 100 and 200. Why? Because it has already taken the snapshot of the database, and after that it will not going to see changes of the database. That's why it now read only 100 and 200. Okay, so now it will write minus 40 rupees on X, and on Y it will write plus 40. Okay, now it tries to commit, but while committing it will see that any of the other transaction has changed something on X and Y or not. So it will see that transaction T1 has changed the values of X and Y. That's why its commit request is aborted, and this transaction will simply revert back. Why it is reverted back? Because while trying to commit, it will see that none of the other transactions should have changed the values of this variable. Okay, here I have extend. Here T2 tends to write on X and Y, but they are committed after this transaction starts. Hence, this transaction is rolled back. Okay, so transaction T1 has changed the values of X and Y after T2 starts. That's why it is reverted back. Okay, so here it also tells about the rules that first committer wins. First committer wins means, like let's say in this example, let's say T2 has already committed before committing this transaction. So if T2 has committed this transaction, then when T1 tries to commit this transaction, it will be reverted back because because it will see that T2 has changed the values of X and Y, which is trying to write on the database. So it will simply revert back. So in this case, always the transaction which is committed first, like both transaction wants to write on same variable, then transaction which is committed first, it will be exist in the database, and another will be reverted back. Okay, so this can cause a major problem also. So we are going to like what are the benefits of snapshot isolation. and also the problems with the snapshot isolation. Like, what are the benefits of snapshot isolation? Why we are doing this? Like, so let's look at this. So there is no possible. So in the two-phase locking, we have already talked about, like, there is the possible case of deadlock also, which is very hard to handle, like which is very difficult. We can say it can add a lot of overhead to handle those deadlocks also. But in this snapshot isolation, there is no possible scenario of deadlock. Transactions are less likely to block each other. Or simply, yes, they do not block each other. Here, no transaction can block each other. It is only at the time of commit it is aborted, because if another transaction has write something which is breaking the integrity rule or something. Okay, so here transactions are less likely to block each other. Also, reading is never blocked. Here, reading is never blocked simply. Yes, because if some, let's say, transaction T1 wants to read only, so transaction T1 is never blocked by transaction T2. Okay, it is never, any of the transaction is not block, cannot block this read transaction. It is only it checks only the write conflict. That's why reading is never blocked in this snapshot isolation. Hence, improved read performance and allows more transaction to occur concurrently. It is easy to implement. It is quite easy to implement this snapshot isolation compared to those two-phase locking or multiple granularity. Okay, and also it minimizes the conflict checks. Only check the write conflict. Yes, this I haven't talked, but in snapshot isolation we only check the write conflict. Like, there is the possibility where read write conflict also happen, because it never checks, like, while reading this x and y value, another transaction has changed the values of x or y also not. Because here, if we see, like, while reading the values of x and y, some other transaction has changed the value of x and y, still we are reading the previous values of x and y. So however, snapshot isolation do not check this thing. It only checks the write conflicts, like, while it only checks the own variables in which this transaction has written something. So it should have those variables should not be changed by any other transaction. Okay, so it only sees the write conflict. It never sees the read write conflict. Okay, this is very major thing. Like, that is, like, it never handles the read write conflict. It only handles the write conflict. And what are the problems with the snapshot isolation? So problems with snapshot will not always give a serializable schedule. Yes, because here if we see that these are not the serializable schedule. You cannot serialize the schedules. Okay, not here. Here, if we see here, we can see that, and these are not serializable schedules. Still, we are doing snapshot isolation. So, mm, snapshot snapshot isolation will not always give a serializable schedule. Also, transition takes decision on outdated of snapshots of the database. This thing. Uh, I have already talked about this thing, and also there is a skew right problem. Like transaction T1X, let's say there are two transactions. Okay. Let's say there are two transactions, T1 and T2. So in T1, there is one, it won't tries to execute x equals to y, and in T2, it tries to execute y equals to x. So let's say in database, initially it is having x equals to 15 and y equals to 40. So both transactions starts at the same time. Okay. In the case of snapshot isolation, we will find that, so what will happen in the case of snapshot isolation and serializable schedule? So, okay. So in serializable schedule, either the both variables will have the value 15 or both will have value 15. We can execute. It depends on the which transaction executes first. So if transaction T1 executes first, then both values will have value for both x and y variables will have value 40. And if transaction T2 executes first, then both variables will have 15 value 15. Okay. But in case of snapshot isolation, we will observe that the values are simply exchanged. Why these are exchanged? Because both have taken the snapshot with each other, and they are not going to conflict with each other. Why they are not going to conflict with each other? Because transaction T1 is writing on variable X and transaction T2 is writing on variable Y. So both are not conflicting with each other. Okay, this is a read-write conflict, but snapshot isolation is fails to handle this read-write conflict. Okay, so let initially x equal to 15 and y equal to 14. Okay, so in case of snapshot isolation, we'll find that it leads to an exchange of values. In the case of serializable schedule, it leads to both x and y have the same values, either 15 or 40. It breaks the serializability when transaction modify different items based on the previous state of other items. That is read-write conflict simply. Starvation. So there is a problem with starvation. So I have already talked about the starvation. Like in case of first committer means like let's say whenever this transaction tries to commit on variables x and y, some other transaction comes and commit on the uh, like come change the variables values of x and y. Like this is a long transaction. Let's say this is a long transaction. So while happening of this transaction, there are very many more transactions which commits too fast. Like so, it can there might be a case that this transaction has aborted more many times this transaction has aborted just because another transaction comes and commit on those variables on which this transaction wants to write. Okay, so this was the starvation. So first committer wins may lead to the continuous rollback of the same transaction many times. This is the problem of starvation also. So these are the end of slides. Okay, thank you.